Hi, everyone. Thanks for coming to the last talk of the day and spending it with me. I'm Anna. I work at Neoform in the department called Neoform Research. And for me specifically, that means that I get to work on Node.js core full-time, which is pretty cool. That like ADDALEX, that's my Twitter and GitHub handle. So on the schedule, it says that the slides will not be uploaded, but I did check the box for uploading it on the conference website. So I guess they will appear there. I will also post a link on Twitter if you want to look anything up. Yeah. Like I was introduced, so I did just come in from California. And well, yesterday when I was on the train into the city here, I overheard people talking about how sunny it is in London. I mean, I guess, but yeah. But anyway, let's talk about character encodings. So this is a screenshot from a Travis CI run that I ran a while back. It's not that long ago. It was earlier this year. But this bug has been around for a long time because I gave a talk about this topic in 2017 in March. And they had that bug there already. And I don't know who of you can tell why there are these replacement characters just like randomly in the middle of the text. If you can't, that's good because hopefully you'll learn it right now.
It means that they can't be resolved.
Yeah, give me a second. So let's go back a step and think about, so what is a character encoding? In the end, when people do things with computers, they tend to work in text forms, whether that's like programs or whether that is some other kind of input that they give to the computer. It's usually text. And text is conceptually a list of characters. Like that's what separates it from just random images on paper. And the idea with character encodings is, so computers definitely prefer numbers. So we take these characters and we assign them numbers, integers, and then we figure out a way to transcribe those integers into a list of bytes. And that whole process, like going from text to a list of bytes, that is known as encoding, and the reverse step is known as decoding. So for example, this would be the standard ASCII approach to this. So like hello is a 5-letter word. We will split that into 5 separate characters. Each of these characters is being assigned a number. And then, well, at least in this case, we just take these numbers and say, OK, each of these numbers corresponds to 1 byte in the final output. But like once you start working with more and more characters, that system kind of breaks down because when you say each character is 1 byte, then you're stuck with 256 characters. That doesn't work for more complicated use cases like Chinese characters. So what are we going to do about that? So yeah, the simplest version that you can do this is ASCII, or at least historically, it's the most important one of the first character encodings that came into existence. And the idea is, OK, yeah, we take about 127 characters. Not all of these are like printable characters that you could see on paper, but still. And we assign each of them numbers. So like these are the decimal and hexadecimal values that we give them. And we say each of these values will just be encoded as a single byte in the final output. Yeah. I will use hexadecimal representations a lot in this talk. It doesn't really matter because the exact values don't matter, but yeah, just as a heads up. And so like ASCII is a 7-bit character encoding, and it covers most use cases that appear in English languages and like languages that use a similar alphabet, which aren't all that many. And that's pretty much it. Like there's not a lot else that you can do with it, which is kind of frustrating when you do want to support other languages. Yeah. And as a side note, so like there are other character encodings that historically were like concurring with ASCII. So for example, there's EBCDIC, which is basically only used on IBM mainframes these days. And I was thinking like for April Fools this year, I might want to open a PR against Node that has support for that character encoding. Because, well, again, only supports IBM mainframes. It's not really in use since the 70s, I guess. And well, reality is stranger than fiction. And now we actually do have an EBCDIC encoder in the Node source tree anyway, because we actually support one of these weird IBM systems, or start supporting them. But yeah, anyway, so the first step towards making ASCII work for other languages is to extend it. And so the idea behind a lot of the character encodings that came next, in particular the ISO 8859 something ones and Windows code pages was, okay, so ASCII is 7-bit, which means we have another 128 characters available. And so we're just going to create a lot of character encodings that cover some specific languages. So for example, there's Latin 1, which stands for ISO 88591, but rolls over the tongue a bit more nicely. Yeah, so that is for Western languages. Like you can write Spanish, French with it, languages like that, German too. Yeah, and then there's other encodings for other languages. Like there's a Cyrillic variant in that standard. There's a Cyrillic Windows code page. And these are not necessarily compatible. So like, this is an example where there's characters in 2 different character encodings for the same languages, so both for Cyrillic languages. But if you encode something as one of them and decode as another, it will come out as garbage. So that was also not a great situation overall. And again, this doesn't really cover the, like, for example, Chinese character use case. Something that people did for that, so this is just one example of a character encoding that was used for Chinese characters, is GBK. And so the idea is, okay, 128 extra characters, that's not enough, right? But we can say, so if there's a character that's not ASCII, so like with the upper bit set, then the next byte will also count towards this character. So it's either 1 byte ASCII or 2 byte Chinese character. So like that gives you about 30,000 more characters, which is still not enough to cover all of the Chinese characters that exist, but it's practical enough. But yeah, so basically the situation that one ended up with was like, so there are hundreds of character encodings out there, which is not an exaggeration actually. And so let's work on something that works for everybody. And so, well, I mean, this XKCD decoding is obviously somewhat sarcastic, but for character encodings that actually worked. So what we ended up with is Unicode, which is not an encoding. But it is like, so it is a character set, which says each of these characters, each of the characters in the word million, which I chose because it has, well, a non-ASCII character in it. To each of these characters, we assign a number, and that is Unicode. And that should ideally cover all the use cases that were previously covered by other encodings. And then we specify an actual encoding, and there are multiple of those, which define how to translate these integers into byte sequences. So like there's UTF-8, UTF-16, UTF-32, and quite a few others. Like UTF-8 and UTF-16 are the most important ones, and definitely the most important ones for JavaScript. So like, yeah. So the way that Unicode characters are usually spelled out is, so U plus and then 4 hex digits, or 5 sometimes if the character is, doesn't fit into the 4 hex digit range. That is how you specify, okay, this is the character I'm talking about. Does not specify how it is encoded. The numbering is compatible with Latin 1. So like the first 256 Unicode characters are the 256 Latin 1 characters. That's actually kind of important for JavaScript too. And so the maximum number that one can have is like larger than 1 million. So we'll have a little more than 1 million characters in total available for Unicode. Hopefully that's enough for the future. Yeah, we'll see. Right now there's like no issue with with that. It also includes an emoji, which is, I guess, something that the Unicode standard is kind of famous for these days. So like every new reversion of the Unicode standard comes with new emoji. It has its own replacement character, which is something that previous character encodings didn't necessarily feature. So like there's a special character that can be used when something cannot be decoded successfully. And this is also the character encoding that we talk about when we use character escapes in HTML or in JavaScript. Like that always refers to some Unicode code point. The most common character encoding that is used with Unicode is UTF-8, which is, well, it's a variable length encoding that for like the higher and higher the character number is, the longer the byte sequences in which it is encoded. And in particular, it's ASCII compatible. Like the ASCII characters in UTF-8 are the ASCII characters as they are encoded by ASCII, which is very nice. And it's also a nice property of using the scheme, like these particular byte sequences don't really have to worry about how the actual bits are encoded, but if there is something broken, some invalid byte in there when you decode it, that won't break decoding of the rest of the string. So for example, if we encode a string using Latin 1, again, this mul string, and then we decode it as UTF-8. So this FC, this is not a valid byte in UTF-8. Never, ever it is. And so what we can do, we can actually just replace it with this replacement character instead of having it gobble up all the rest of the string. Then there's UTF-16, which uses 2 bytecode units, so like 650,000 characters that can be encoded like in a single 2-byte unit. Ones that do not fit into that range, they are split into 2 separate pairs of code units. And because it uses 2 bytes, there are 2 different variants. I don't know if you are familiar with that, but there's generally like little endian machines and big endian machines. Some of them put, like the little endian ones put the low byte first and then the higher value byte. Big endian, the reverse situation. Most modern processors use little endian, so that's, for example, why Node.js only supports that variant. Yeah. And one thing that can be used in this case, well, sometimes is used in this case, is a special character, which is called the byte order mark, which is sometimes prepended to a UTF-16 string so that you can figure out, okay, this is little endian or this is big endian, just by looking at the first bytes of a string. And so when we were talking earlier, just before this talk, me and Richard, he was like, well, JavaScript still uses this 16-bit encoding scheme. And well, so sometimes I hear people say that JavaScript uses UTF-16, and that's not quite correct because it doesn't, the spec doesn't tell you how the characters are actually encoded in the engine. It doesn't tell you anything about that. But it could be UTF-16. And generally, JavaScript engines are very clever about this, so you don't really need to worry about it. Well, we do use character codes from 0 to 650,000, 65,000, sorry. And we do split code units that don't, like code points that don't fit into that range into 2 separate units. So for example, if we use emoji, which generally don't fit into that, that basic set of characters, then we will split them into 2 separate ones. So in a way, JavaScript uses, it uses a string representation that is very much based on UTF-16. But again, how the actual representation looks like, the spec doesn't say anything about it. And so so for V8, I know this because I work a lot with V8. SpiderMonkey, Firefox's JavaScript engine seems to do the same thing. Well, they do have a representation that works for Latin 1 only strings. So if your string is mostly ASCII or mostly Western Latin characters, then it will probably try to use that representation instead to save space, to save memory. Yeah, but again, like, don't overthink it. There are tons of different string representations in modern JavaScript engines, and yeah. So the way that you use these character encodings in JavaScript, well, the very basic thing you want to do is you want to convert between a string and you want to convert between a list of bytes, which in JavaScript is usually uint8 array, or in Node.js a buffer, which is also just a fancy kind of uint8 array. In Node.js, what you can use is buffer.from to encode a string into a buffer, and then use buffer.toString to do the reverse transformation. The browser has text encoder and text decoder APIs that allow you to do that. So you can create instances of these classes, text decoder and text encoder, and call encode and decode messages. And they perform that conversion also between strings and uint8 arrays. And modern Node.js versions also support these. Like Node 12 have these as globals. For Node 10, you need to require them manually from a module, but still. One thing to notice there is that, so text encoder supports a wide range of encoding, which makes sense because browsers have to support a number of legacy encodings as well anyway, because they have to read legacy websites in those encodings. But for encoding, they only support UTF-8. So that's very much pushing people towards using UTF-8 everywhere, which is generally a good thing. And if you ever wonder about what happens when a text decoder encounters something invalid, well, usually it just replaces it with a replacement character sign. So like this 0xff character that is, again, never valid UTF-8. You can also pass a flag to it that says, hey, please throw an exception if there is something wrong in that string that cannot be decoded. I don't generally know why you would want to do that, or at least not if you actually want to decode a string. You would probably only use this for testing whether a buffer contains valid UTF-8 or not. Because if you want to decode a string, like, you can usually just live with a replacement character showing up. It's not an ideal situation, and something went wrong somewhere, but yeah, you still end up with something that mostly works, and that is your goal, right? But anyway, let's go back to that. So one of the reasons I picked this particular example is that this kind of problem is something that pops up in our Node.js issue trackers on GitHub from time to time, and it is something that even Node core contributors get wrong, or tend to get wrong from time to time when writing tests for our test suite. So what is wrong with this code example? And this is a Node.js code example, but you could figure out something similar with text decoder in the browser. Well, the first thing that I'm just noticing right now is that data should have been let instead of const, but let's look over that. Okay, so there's a string. Whenever standard input gets some chunk of data, some buffer, we append it to that string. And once the standard input is all read, we write it out again. So Unix has actually a command like this that's called sponge. It's like it sponges up all the data and then presses it out at the end when the input is done. But anyway, so what is wrong with this part of code? So the first hint that I can give you is that, so when you concatenate a string and an object, and the buffer or uint8 array is an object, then it will call toString on that object. And well, yeah, in this case, it always calls it on the buffer. So we call .toString on each individual buffer here. Okay, so what is the case in which this can go wrong? So we don't, yeah?
I thought to ask us a question.
Yeah, questions at the end, I would suggest. So what can happen is we don't control the size or the boundaries of the buffer chunks that we read from standard input. So for example, when the input is mil, what can happen in the worst case is that it gets split right in the middle of the UU character. So for example, we could read from the operating system first 2 bytes, then 3 bytes. And when we call toString on these individually, it won't work because each of these contains parts of a valid character, but not an entire one. So we will end up with M replacement LL, which is what happens here. So what Travis CI actually does internally, probably, is it reads data from the terminal that it created, and it converts it to a string, and it does it for each chunk that it reads. Which is, because these chunks are usually rather large, I would guess like a couple of kilobytes at least. It doesn't happen for every single character in the output, and it doesn't happen when you happen to not hit a character boundary. So it works 99% of the time, but sometimes it fails. And that's what's happening here. So the way to fix this in Node.js is very easy, actually, because strings have a set encoding method that basically tells the stream, hey, I don't want to read buffers, I want to read strings, and I want to read them using this encoding that you use to decode the buffers. And it will take care of decoding automatically, and it will take care of cases like the one that we just saw where, partial characters might be read. And the way that it works internally is, so Node.js has the string decoder class, which is a very lightweight kind of transform stream-y thing. So you can use it to write buffers to it, and it will try to decode them. And when it encounters partial characters at the end of a buffer, it will wait for the next buffer before it continues decoding. And the text encoder API in the browser actually has a similar feature, which is called stream. So again, streaming decoding. And it will do exactly the same thing. Like if there's a partial character at the end of the input, it will wait for that character to be finished before continuing with decoding. And actually, I think that's kind of a funny pattern that there are some Node.js APIs that were first introduced there that later became browser APIs in a very different format. So for example, we had buffers, which in the browser were later introduced as uint arrays, or in the language generally. Same with string decoder and text decoder. Same with streams and YWG streams and so on. But yeah, like I said, so JavaScript uses the same pattern as UTF-16 for dealing with characters that don't fit into that basic 65,000 character range. So for example, when I take a clown emoji, that is actually 2 separate units in JavaScript. And the string length will be reported as 2, so well, not characters, but 2 units in that string. So how do we actually get the actual number of the characters? How do we work with this fact that every entry in a string is not necessarily a single character? So there's an easy option for doing this. And so strings in JavaScript are iterables, which means you can expand them into arrays, and you can iterate over them with for of. And that will do the right thing. So for example, when you expand a string like that, it will give you an array where each individual entry is also an individual character, even though that last one is actually made of 2, character codes. Right? And again, if you want the number of characters in the sense of Unicode code points within a single string, you can use for of to iterate over that. It's not maybe the prettiest thing in the world, but it is definitely more accurate than string.length for this case. And the other options, so JavaScript has some APIs to do manual extraction of code points from a string. So yeah, a long time ago, all we had was string.charcode add and string.fromCharcode, which it did the right thing in the sense that it gave you the content of a string at a particular index, but it didn't give you the code point in the case that it didn't fit into that, again, 65,000 character range. And so some newer APIs were introduced, which are called .codePointAdd and string.fromCodePoint, which basically deal with these the way you would expect them to. Like if their character doesn't fit into that range, it will decode the entire character and tell you, okay, so this is the actual Unicode code point, the actual Unicode number associated with that character. And so this one is also an issue that sometimes pops up. Not that often, but it's one of these things where you're like, if you don't know why this is happening, then you don't know. And if you know that this is happening, then you know. And you're like, wow, wouldn't have thought that. Or at least I was. So we have two regular expressions. One checks whether an E occurs in a string 2 to 4 times. One whether the cat emoji occurs 2 to 4 times. And it works in the case of the E, and it doesn't work in the case of the cat, which kind of looks surprising, to me at least. And well, the reason that this is happening is that so the cat emoji, again, it's 2 separate units. And the way that JavaScript interprets that string is like, so it says the first half of the cat once, and then 2 to 4 times the second half of the cat. Which then doesn't match that 2-cat example. And there's an easy solution, luckily. So JavaScript regular expressions have received this Unicode flag that you can set on them, which is just a small u. And it basically makes this work correctly. And it's generally something that you want to set on regular expressions. Like, there's no reason to ever not do this. And then also, so when I first heard that JavaScript regular expressions had Unicode support, I was really excited to see if they had like character class support or something like that. And back when they were first added, they didn't, but now they actually do. This is not supported like in all browsers yet, so apparently, sadly, Firefox, which I personally use, doesn't, but it's going to come at some point. So you can use this \pescape to figure out information, to match characters based on some metadata that exists about them. So like there's a ton of different Unicode classes of characters. For example, this one, emoji presentation, that's, well, yeah, you can use this to actually figure out very reliably what characters in a string are emoji. Yeah. Yeah, so another thing that Unicode did, so one of the rules that Unicode has when it introduces characters is that if that character exists in a previous character encoding, and it is separate from like other characters, then it is also going to be separate in Unicode. So like, I don't know if you remember, for example, from the slides where I showed the 2 Cyrillic character encodings, there's a Cyrillic lowercase a and a Latin lowercase a, which look exactly the same. And so nowadays, if we didn't have previous character encodings that separated these two, we would probably not have separate code points for them in Unicode. But again, because there's legacy code out there in the world, they are separate in Unicode. This is not what this is about. This is about the fact that Unicode characters can be composed in different ways. So yeah, I'll show this in a bit more. Like, this is what you get when you try to expand these into separate code points. And for example, with the French name Andre, what you get is you get that A and DR. Those are equal in both of these strings, but in one of them you get 2 separate code points, and in one of them a single one. The reason for this is that so one of them is an E plus a combining accent character, which Unicode features. Like, you can't have characters that you can just put on other characters or below or whatever. Like, I think that's pretty much how you get JavaScript. And you can also just have an E with an accent character on its own. And for the Korean Hangul example below, you get the possibility that, well, I don't know if you know how Korean works, but basically each of these 2 characters, you can think of them as like being composed of 3 separate letters, just like not written in a single row. So you can either have like well, this is the Korean word Hangul, which is the script name. It's like the name of the alphabet, basically. So you could either write as Hang plus Gul in Unicode or Hangul, basically. There are ways to deal with this in JavaScript, luckily. And the way to do that is string.prototype.normalize, so you can call that on any string. And you can basically do the two things that you want to do with them. Either you can make each combined character be as combined as possible, so like the E with the accent as a single one, or the Han as a single one too. Or you can call it with a parameter that's NFD instead of NFC, and that's saying, so like, please decompose these as much as possible. So like E with an accent and two separate ones, or Hang, again, three separate ones. And you may want to like use this when comparing strings, because what you end up with is characters that look the same and that behave the same and that should be equivalent, but that don't compare equal in the sense of JavaScript equality. Going a bit further, there's like two more parameters that string.normalize can take. So another thing that people do, and you might have mostly know this from, I don't know, fancy Twitter handles or Twitter names. So like you can use characters that are variants of base characters. So for example, this word hello, the first time it's written on the screen is with mathematical bold letters. So the way that you would use them in math script. And you may want to be able to figure out, like, so what are the base characters that correspond to this? For this, you have the parameter modes NFKC or NFKD, which, well, they first convert the character to its base variant, and then do the same thing as on the page before. So either combine them or decompose them. And this is something that, for example, you may want to apply this to search parameters, because, well, conceptually, like these strings have the same semantic meaning, right? And yeah, I don't know. So for example, if you were like writing a profanity filter for usernames or something, you wouldn't want somebody to circumvent that just by using fancy letters instead of their standard equivalents. So yeah, like I said, string length doesn't give us the number of characters. What does it actually give us? Well, characters can be composed of multiple characters, so it doesn't give us that. They can be split into two separate units if they don't fit into the basic set of 65,000 characters. And it also doesn't give us the string width. So like if you remember, for that Hangul example, the string length was 6 because it was 6 different characters. Even though it's like, it would only have a string width of, well, 4 because each Far East Asian character would typically be counted as having a width of 2, as opposed to like Latin characters, which in the terminal have, well, they usually have as wide as they are tall, right? But still, yeah, it's definitely not accurate to say that that has a width of 6. So like the only thing that it really gives you is half the byte length when you're encoding it as UTF-16. So like if you ever use the length of a string, like make sure that you're using it for the right thing, because it's easy to use it for something that is accurate 99% of the time, but fails sometimes. So yeah, and like I said, it doesn't give you the string width, which I guess in browsers you can work around that and you will have to account for the font anyway. But for CLI applications, that's a bit different. So for example, Node.js has this built-in console.table tool, which does the same thing as it does in browsers. And it automatically figures out that the emoji that I use here is wider than the other strings in that table. Like it figures out that the second, well, the third column should be a bit larger than the second one. And basically, the only way to do this properly is not do it yourself. You can use an NPM module that does this. It's called string width, and it gives you the right thing. But again, string.length wouldn't. Like it would give you a very unpleasant break in that right border of the table. So if you're interested, I can actually try to demo this real quick. So I have these characters copied here because I don't know how to type them on my keyboard. But so I'm going to start Node, which is, in this case, the master version, but it could also be Node 13. It has the same issue there. So I just typed that string and then dot length, and it works, but the display is obviously broken in some way, and I don't quite know what is going on there. If you use okay, so it's hard to tell them apart when they look the same. If you use the other one variant where they're composed, then we'll do the right thing. Like it won't have this display bug with the autocomplete. So if you're interested and if this talk is really giving you the energy of, hey, I want to work on internationalization stuff and encoding issues, feel free to reach out to me and tell me if you want to look into this. I think it might be that we want to always call .nfc before trying to compute this width of the string. But again, I don't know if that's what's actually happening. Yeah, if nobody comes up to me after this talk, I'll just post an issue on the Node.js repo, but I thought this might be interesting for somebody. Okay, how am I doing on time? There's no clock here. Okay, not too bad. Okay, sorry. So Node.js also has support for string for encoding that you can pass through that is called binary. I'm going to tell you why you should never use it. So in the early days of JavaScript, we did not have U&A array. We did not necessarily have Node.js buffers, for example, in the browser environment. And we still wanted to work with binary data in some way. And so there are two approaches that you can take to that. Either you're going to be like, okay, well, I'm just going to use arrays of numbers between 0 and 255, and that is my binary data type in that case. Or you were using strings. And the idea was that, so you could use use or abuse the code points 0 through 255 to represent the bytes 0 through 255. Which kind of gives you these kinds of strings where the characters are mostly garbage and do not have any meaning. Yeah, please don't do that anymore. U&A array or buffers, those are the solutions that we have for this problem. And if you think about it, so like, again, the first 255 Unicode code points, they are exactly the ones from Latin 1, from ISO 88591. So that is what the actual encoding name is. And if you want to use Latin 1, then be explicit about that fact and don't just call it binary. Because the name is really, really misleading. And again, this is something that pops up under issue trackers a lot. Because people think when they say something with the encoding binary, that it will take the text and convert it to binary. But usually what you want to do for encoding text into binary data is use UTF-8. And not, well, binary doesn't really, it's not a good name for that because all character encodings do that. They all convert text to binary data. And because of the way that Latin 1 is implemented in Node.js, so if you pass in characters that don't fit into Latin 1, it will just truncate off the first half of that, truncate off the higher 8 bits of that character. So what you can actually end up with, and this is a problem that I have seen in the wild, is you can have two Unicode strings which map to the same byte sequence when encoded with this binary encoding, or Latin 1 really. And that's not good, for example, because when you want to hash data or hash a string, you will usually want to hash its entire contents and make sure that it is unique. But if you have strings where two strings map to the same bytes before they are encoded, then you will get two strings that map to the same hash if you use the binary encoding. Again, really not something you want to do. And so I don't know how many of you use Python a lot in your daily lives, but this is kind of one of the things that Python 2 didn't really get right in that. Everybody tried to fix with Python 3. I mean, if you use Python a lot, you already know this, but yeah, so like the original Python 2, its strings were kind of equivalent to these binary strings, and that just really didn't work out the way that anybody wanted it to. And I think the only use case that currently still remains for these is the A2B and B2A methods in browsers that do base64 conversion. Because they do work with binary strings. And that is just because they simply predate U and 8 array. There's no other reason for that. And yeah, so you can basically consider them legacy APIs at this point. So yeah, so for the character encodings that Node.js itself supports, one, there's ASCII, and I really don't know why we do that. Because the way that ASCII works in Node.js, it is, well, when you encode it, it will do the same thing as encoding using Latin 1, but it will cut off the highest bit. So like for Latin 1 characters that are not ASCII, it will just simply give you another one that is ASCII, but that has no relation to the original one. And well, yeah, it basically does the same thing as encoding using Latin 1, but with some extra steps. Yeah, no. Definitely a Node.js regret that we're stuck with for the rest of eternity. But we have UTF-8, UTF-16 little endian. So because most of modern processors are little endian based, so that's a bit easier to use there. Also like because V8 already gives us a way to deal with UTF-16 and UTF-8. We can already use V8's facilities when we don't have to do the encoding or decoding mechanisms ourselves in the Node.js course. There's an alias for UTF-16 which is called UCS2. That is kind of the legacy name for UTF-16 in a way that doesn't support characters outside of the basic 65,000 range at all. Which is basically why you always want to use full UTF-16 at this point. And fun fact, like Node.js does support big endian machines, but on those it actually does manually reverse the byte order when it encodes or decodes using UTF-16. We have Latin 1, which, as I have just explained, it's equivalent to binary, which you should never use. And we have base64 and hex. And this can be a bit confusing because those are not like the others. So like for character encodings, the general thing you want to do is you want to encode text as bytes. So string to bytes is encoding and the reverse is decoding. For base64 and hex, well, it's a reverse situation. It's a, yeah, okay, this is where it's spelled correctly. I have a typo on the next page. So those are binary to text encodings, which means that string to bytes is actually decoding and the reverse is encoding. That should usually not be an issue, but it can be a bit confusing because it means that buffer to from and buffer to toString, they can either encode or decode each one of them depending on what encoding parameter you use. Well, okay, so in the end, everybody uses UTF-8 now anyway, but as you have seen, there are still some issues that you can run into even if you don't worry about this all too much. Sometimes, like obviously legacy code and legacy website exists. I don't have to tell you about that. Sometimes people don't know that they don't use UTF-8. So again, like this sometimes misuse of the binary encoding. Or sometimes they just don't think about it. Sometimes they just notice that buffer.toString gives them a string, and they don't care that it's encoded using UTF-8. Also, so the Node.js file system API supports buffers for the path names, which might be interesting because you would usually expect that for a path name you pass in a string. This has actually been added because our company had a client that did mix multiple encodings in its directory path names. So like you would have a directory with that whose name was encoding using one encoding, and another directory inside that was encoded using a different encoding. Yeah. Well, again, like I said, legacy code, right? So that was actually motivated by a real use case, that you can just figure out how to encode the path into bytes and then submit that buffer to the Node file system API. Because in the end, Node.js interacts with the operating system purely based on bytes too. Like there's no way to pass in strings or anything that conceptually consists of characters. When it talks to the operating system, that's always in bytes, whether that's for file paths or for writing data to a network socket or something. There are never any characters involved, so it's always an encoding step in between. Also, I don't know how many of you use the native C or C++ Windows APIs. They're big, big fans of UTF-16. They kind of made the wrong bet on that before UTF-8 was really popular, I think. So basically, they support so most Windows methods support one ASCII mode and one UTF-16 mode. Like I said, even when you use UTF-8, things can still go wrong. Even the QCon website didn't accept the talk title at first. So like I had to manually edit the replacement character in the middle backend. Yeah. So one thing that I want you to think about, that just like a closing thought for this is, so why are we all using UTF-8 anyway? And the reason, well, there are a number of reasons why it's nice to use UTF-8, but the one big reason is it's backwards compatible with ASCII. Like you can write code for ASCII, and it will work 99% of the time with UTF-8 characters, which is really your goal in the end. You don't want to have to rewrite all of software basically to get to a state of where you have a nice encoding. I truly believe that if we really all made the switch, for example, from UTF-8 to UTF-16 in our applications, we would have a lot less issues with encodings because it would have been a clean break. And anytime you write new code that uses UTF-16, you would have to think about how this affects your application. But the world as it is a big fan of backwards compatibility, and where you can write code the way you're used to it and not have to think about this. So yeah, that was it. Oh yeah, actually, I have a list of resources, and I did want to show some of them. So one thing that I used a lot during this talk is the Unicode command. That was me, was it? Anyway, so you can do pretty cool stuff with that. Like you can give it a string, and it will tell you the Unicode code points, how it looks like when you encode it in some ways using UTF-8 or UTF-16, what categories it's in, all that kind of stuff. You can also do the reverse thing. So you can get all the cat faces by grabbing for it, basically, using the cat face regular expression. I didn't know there were that many. But yeah, it's a super handy tool for if you're dealing with Unicode characters in general. There's also iconf, which basically is a character encoding conversion tool. So I can say, echo hi, I can pipe it in there. And okay, so this won't work because, because my terminal is configured to use UTF-8 as everybody's terminal should be. But for example, we can hex dump it, and then you'll see, okay, so it does prepend this very special character, FFFE, to make clear this is the byte order mark, this is the byte order that we're going to use. In this case, it picked little endian. And then okay, so this is the actual string. This is the actual string when encoded as UTF-16. And then there's a new line afterwards. But anyway, yeah, so iconf is great. There are also node bindings for it if you really need to deal with weird character encodings. I have a list of MDN pages that are pretty useful, but I guess you would be able to Google them yourselves if you want to, if you want to learn about something. There's also the Node.js buffer API docs, which are okay. I did go through them a couple times for this talk, and I definitely picked up a lot of things that should be explained a lot better. But yeah, this is it. Again, Twitter handle is ADDALAX, and I will upload the slides and post the link and everything.
Okay, question.
Sure.
We Sorry, we just have time for one question, actually.
Okay.
Unfortunately, we've run out of time, so, but please
Sorry.
go ahead.
Okay, let's say I'm about to create a site where people from all over the world can make comments on movies in their own language, and I will ensure that there will not appear any question marks on the screen. Or should I use UTF-32 then, or what should I use?
Well, at the points where you need to deal with encodings, you should always use UTF-8. Like UTF-8 does support the full range of Unicode characters. It supports exactly the same ones as UTF-32 or UTF-16. Yeah, the issues only pop up basically where, like the question mark issues, the replacement character issues, they only pop up when you mix different encodings. And because everybody's basically standardized on UTF-8 right now, you will want to use that for everything.
Okay. So if I store the comment in UTF-16 and I present in UTF-8, I will have problems.
Yeah, if you mix those, if you decode with one and encode with another, that's not going to work out. If you have any other questions, I'll be available anyway, right?
Okay, thank you very much. And thank you very much for coming to the JavaScript chat. Thank you.